Because who knows?
Turn another one of those things on.
So it's just a Bluetooth speaker, right?
Yeah. Looks nice.
So you're selling them, or
No.
you bought a bunch of them?
Yes.
So you bought like $300 worth of speakers?
Yep.
His work wants them.
Yeah.
Oh. Like, look, I have Tylenol and Cheerios to move.
You see, Dover does it more like a family-friendly fashion. He makes them in like pixie sticks.
It is actually a brilliant way to sell cocaine.
That's on recording. That's just a brilliant way of selling cocaine. I don't know about you people. It's like, what do you mean, you people? All right. That was an icon for an app.
Original Coca-Cola.
Oh, the app is Aunt Jemima's.
That could go anywhere.
Syrup?
No, you know Aunt Jemima.
Syrup?
No,
Syrup.
it's Mr. Gonzalez's girlfriend.
Also syrup. That's right.
The wedding is next Sunday, a week from this Sunday.
Wasn't invited?
Well, it's an at-sea wedding.
And I wasn't invited?
It's gonna be in the Caribbean.
Can you videotape it?
I will.
You couldn't afford one of the lifeboats on the cruise.
All right, so let's.
How do you need a lifeboat? It's pretty expensive.
You see him sitting on the cruise ship as it's going down. $10.
Oh no,
Get jewelry, everything. Yeah, let's go.
Gotten for your life.
All right, let me get over to. All right, so we'll start with this. So everybody read about sockets, like preparation for a quiz.
The introduction chapter. There were like 4 chapters on it though.
Yeah, did you read all 4 chapters? How long does it take to read 100 pages?
What is this?
What do you mean by what? How do you do air quotes for reading? What sounds like the inner meaning thing? It's like, look, typically I use papers for the Tylenol Cheerio thing. Okay, so let's. So tell me, what did we learn about sockets?
Client side, server side, like make a connection using addresses and need to be binded to each other.
Okay, what kind of addresses? Oh, okay, that's an interesting response. Tell me more.
Well, I guess the 3 overarching domains would be
The overarching domains.
Sure. So Unix, that would be because everything is like files. It would be the file system path. Then there's the IPv4 addresses, which those are the 32-bit ones plus like the port number, and then also for IP6, that's the like 128-bit ones. Port number.
Okay, so there's an IPv4 and an IPv6. What's the difference between those two?
Well, didn't we make the V6 because we were running out of IP addresses?
Yeah. So and what's somebody else? What's an IP address? What are those guys?
The address of a device on a network.
Okay, so it's like a unique telephone number of a device. Okay, and specifically it's for TCP/IP network protocol, right? Okay. Is this thing like flashing? Is it doing weird stuff up there?
That's the light.
Oh, I can't tell if I'm blacking out or not. Yeah, just second from the top,
He put some of the Tylenol Cheerios.
and then just mash your fingers on. No. You're good. Did you hit the second from the top?
Yeah, that was the one.
It dimmed. You have to dim more.
Mash all the buttons.
Slash all of them.
Yeah, just go 1, 2, 3, 4.
Try the third one.
Number 3 in the middle.
Which one?
Darker. Darker.
Turn all the way on.
Go.
There
All right,
we go.
perfect. All right. So an IP address is kind of a unique phone number for a computer on the internet. It's probably a pretty good definition for us and kind of what we're talking about here. There's kind of two different domains that exist today. IPv4 is kind of the one we still use, but there's been an introduction of something called IPv6, which just uses more bits to represent that telephone number. And the reason we had that is because we started running out of IP addresses. Why did we run out of IP addresses?
Too many devices.
Okay, so you think that the number of IP addresses we have,
Because of the protocol that we used to name them, we ran out of them.
okay, so we have, let's open up our keynote here. What happened?
You're making Donald Trump jokes.
Oh, very nice.
Yeah, I did. He's doing just fine down there.
Why do you know that?
He
He
said
said it
Well,
himself.
the Republican presidential debate.
I know, I got you.
Yeah.
Sounds pretty. I mean,
Pretty standard for me.
yeah.
I have to say the best, one of the best quotes that came out of it that was in the news this morning saying, "We really can't fact check that." We're sorry.
At least he didn't do the whole. This is going to be huge.
So that's it. Now we need to see his girth certificate.
All right, so IP addresses. Let's actually do IPv4. So we have 0 to 255. So this is 8-bit, dot 8-bit, dot 8-bit, dot 8-bit, right? So that's a 32-bit address. And not all of those addresses can be routable. There are specific addresses for, this is more of a networking class type thing, but there are some non-routable IP addresses. So all the 10 numbers and all the 192, 168, all those numbers are also, yeah. Also, then there's 168s that are reserved for DHCP non-errors. But for the sake of this argument, they're all unique IP addresses. We're just going to use that. So this is 32 bits. So that means we have 2 to the 32nd unique IP addresses in the world. All right, and so that's what, 4 billion? 4 billion IP addresses is 32 bits. Positive, negative. We don't need positive. We don't need negative numbers. So it's a 0 to 255. So it's for integers. Size of int is negative 2 billion to positive 2 billion because it's 4 bytes. But we only have positive numbers here, so it's 0 to 4 billion. So 4 billion unique devices. So the question is, do we actually have 4 billion unique devices on the internet, on the planet? What do you think? Think we have more?
Oh yeah.
It's either that or we will run out.
What's the population of the planet?
Like 8 billion.
7.5. Okay, so and a majority of that population density is in kind of areas of the world that probably don't have iPhones at this point. Realistically speaking, we probably do not have 4 billion unique
That's
devices.
assuming that it's one IP per person, but I mean, you get
One IP per person, right? So most of our networks are handing out DHCP addresses, right? So how many of you have a home network that has 3 or 4 devices on it? You know, a lot of us, right? And each of those devices is getting a 10.0.0.100 address or something, right? So at my house, my laptop might get 10.0.0.40. Tim might have the exact same IP address handed to him at his house. Well, that doesn't mean our addresses are conflicting. We are local. We have unique addresses in our own networks. All right, so we can double dip here. So the reality is we probably have not used up 4 billion unique IP addresses. But why are we out of IP addresses? How are IP addresses handed out? Concordia has, we have a block of IP addresses here, right? So if I hold down the option key here and I click on this, so here's 172 addresses. Well, actually, are internal routable, but whatever. Let's just pretend those are unique addresses. How do we get that address? Well, we just text Al Gore on his flip phone. All right, so we have to when an organization needs real routable IP addresses, a static IP address, those have to be requested through ICANN. ICANN. Stands for something, I don't remember what it stands for. But in any case, you request this block of IP addresses, and depending on the size of your organization, they give you a chunk of IP addresses. Now, they don't give you a precise number of IP addresses. Like if you need 18, they don't give you 18. They give you the next thing greater than 18 that will match into a block of IP addresses. So there's a bunch of IP addresses they have reserved for places that aren't using them. There's a whole bunch of IP addresses that are just sitting there wasted, is the punchline. So we haven't done a very good job of sending these things out. So IPv6 just says, oh, we're going to fix this problem by just creating more unique IP addresses. No problem. When in doubt, just double the size. I think, is that a... Yeah. And that's a Trump thing too, right?
Sure.
Yeah. Huge. All right. Because he says U's weird, right? Or H's.
Yeah.
Yeah.
Almost as if it were a Y.
Yeah.
Haven't you met him?
I have. Actually, I hadn't talked to him in years, but we used to be very good friends. True story.
You're saying.
Yep.
Facetious. Good
No.
friends.
Dead serious.
Good friends.
Yeah.
With Donald Trump.
Mm-hmm.
How?
Well, a lot of you know that my family business, we had a real estate company. And we still have the company, but I don't write software for it anymore. But we used to travel around the country doing like real estate conventions, selling our software to real estate investors. So we were at a lot of these conventions. We were the kings of residential real estate, and Donald Trump was there as the king of commercial real estate. So a lot of times we shared the stage, so we got to know each other at those things, and so it's interestingly, he's a very different person in real life than he is on TV. That doesn't mean that I don't think he's a complete freak show with what's going on right now, but my perception, I haven't talked to him in a while, but my perception is that it is legitimately all a humongous act, which also seems not presidential, but at the same time,
Maybe you should give him a call.
huh?
Email him.
I'm sure he's not reading his own email anymore. So who knows?
He probably got private service.
I actually, I do have a private cell phone number. I assume it's still his number. I don't know. He's changed it in a while, but
I think he did. He just had a beef with who was it? You know what I'm talking about? He had a beef with someone, and he released their phone number to the public.
Oh, yeah.
Who was? It wasn't Chris Christie. Oh, it was Ted Cruz, I think. Oh, Lindsey Graham. Yeah. So Lindsey Graham was gonna ask Donald Trump for a bunch of money, and Donald Trump said, "No, I'm not gonna give you a bunch of money." For when he was gonna run for the presidential thing, and then he kept asking him. So Trump tweeted his phone number, his personal phone number, and said, "Give him a call. He's looking for money." So then Lindsey Graham did the same thing to Trump, but then Trump just changed it to forward to a donation thing.
oh, the phone number.
Yeah. So
Gotcha.
like,
He forwarded it to the Pope's home number. All right. So in any case, we have a bunch of different ways that we can connect our sockets together. Generally speaking, when we're thinking about connecting, so is that another one?
There's a gif of him, except his hands are like super
Oh, yeah.
small.
So, I can't wait till this election is over.
You only got
I know it's like
4 months,
we have months, don't we?
8 months.
Yeah, I mean it's not even close.
Started yet.
Why the heck is it like such a big deal right now? Can't we just pull a name out of the hat and move on with life? So in any case, in any case, when we talk about sockets, in our perspective, what we're mostly talking about is what if we have two processes that are living on different computers, talking to each other. Now, realistically, from our perspective, we're going to have trouble testing that because Cloud9 probably does not have a public IP. Although we might be able to hit it by, we'll have to see. But at the very least, we can pretend like we're hitting it from a different address because you can just use localhost or 127.0.0.1 as the IP address. And that'll just loop back and not have to worry about going through a firewall or anything like that. So we could fake it, but generally speaking in our world, a socket is like a pipe. Tylenol Cheerios hashtag. It's like a pipe, but it's connected two processes across the internet instead of two processes on the same machine. Make sense? All right, what else can you tell me about sockets? So you said read write. So we have an upload and download stream. So it's a two-way street for sockets.
So there's two different types of sockets, the datagrams and then the streams are the ones that are bidirectional.
They're better?
I said bidirectional.
Oh, bidirectional, okay. And what about the datagram? What's the purpose of a datagram socket?
Also, the streams are more reliable. Datagram, pretty much what I got out of that is that they're less reliable. You can't be certain that they're going to get there.
Okay. So who would use datagram sockets? If you had the choice to use, if you had the choice of using standard bidirectional sockets or datagram sockets, which would you choose? Would you ever choose a datagram socket?
I think doesn't like voice chat type stuff or video streaming use UDP?
Yeah, it's UDP. Yeah. So UDP, the UDP protocol uses datagram sockets because those types of things are single directional. We are streaming data one direction. So when you're watching YouTube and data's flowing towards the screen, you don't want everything to pause because of one missed frame, right? You kind of like, we missed the frame, that ship has sailed. Keep having more frames flow in so this video seems reasonable. If I miss one frame out of my 24 frames in a 1 second period of time, I might not notice. I might have been blinking or something like that, who knows, or we might be pebbles. Hashtag blind.
So the stream in that scenario would like wait for you to get that frame and then it would keep going? Or?
Yeah, if you were using sockets, bidirectional sockets, well, if we abstract the layer, underneath the hood, UDP protocol uses datagrams, TCP/IP protocol uses streaming sockets, bidirectional sockets. So if you use UDP, it's non-blocking. We missed it, that the opportunity's gone.
Fire and forget.
Yeah, TCP, phrasing?
That is fire and forget.
That's right.
Yeah.
All right, so in any case, TCP/IP guarantees the arrival of data. Therefore, we cannot miss bits. Well, we say guarantee. It will not complete unless everything has gotten there. So it's possible if you have literally a break in the internet that the data will never arrive, but it will never think it has arrived either. So you are guaranteed that everything will arrive and be re-put back together in order. That's part of the TCP/IP protocol. It gives up performance at the cost of reliability. Okay. From our perspective, we don't necessarily care. It's more of a networking type thing. But so for us, when we think about sockets for inter-process communication, typically we're going to hold at a pretty high level the idea of that all the data we send arrives. That's kind of important to us, right? So we're probably talking about bidirectional traditional sockets where they have an input and an output stream, and anything we write to them, that's effectively our pipes, right? A pipe had an input and an output. We can read and write from a pipe using our standard standard read and write generic I/O protocols, I/O functions. The stream socket's going to be the exact same thing, except once we establish it, we might be writing over the internet rather than across two processes on the same machine. That's the advantage of sockets. Okay, so last time we were looking at pipes and name pipes. Well, we looked at pipes, and I said we'd look at name pipes, but unfortunately we missed last class. I apologize for that. My wife had a big dental appointment, and I had to drive her. She was on sedation stuff. So in any case, let's kind of zip past that real quick. We won't actually use name pipes. We'll just talk about them. I think at the end of last class, what we saw is that we could, so we didn't go quite this far because this would have given away the punchline, right? So we saw this at the end of last class, that we were able to create a pipe. We would register that pipe with the operating system. Then when we forked, that pipe was shared. And why was that? The reality is that when we think about what happens, what kind of information is shared between our parent and our child, did we actually share the pipe? Or did we just have an integer that was our unique identifier of that pipe, and the parent and child both got a copy of that integer? It wasn't the same integer, it was a copy of it, but it both had the same value in it. And that value is what uniquely identified the pipe we were using in the operating system. Does that make sense? So because we asked, this is really a singleton, isn't it? We asked the operating system, we said, hey, I need you to register a pipe, tell me the ID. Thank you, I'll let all my children know. So from that point forward, when he forked Abe, yeah. What's up, Christian worldview? Hashtag Christian worldview. It's been a new thing. Yeah, I'm working on it. Usually I can make things popular. We'll see what happens. All right.
Pretty well with this Twitter thing, yeah?
Which?
Yeah, the Twitter. You're blowing off the hashtags.
Yeah, they really picked up that hashtag.
Oh, hashtags from Twitter? I didn't know that. I thought it was from...
I thought it was from you, and then Twitter just made it. They took the
Twitter stole my hashtag thing? Okay, so in any case, when we get, so we notice up here, here's our pipe, and for our file descriptors, and we use an int, and when we wrap that with our pipe command, that makes this guy something special. Okay, then when we fork, notice we duplicate the parent's file descriptors. So we do get a copy, but because that guy is an int, it's not a pointer. We're not going to some memory address. Instead, we've registered something at the operating system that's like a singleton, and now our parent and child can now both go through that and still have access to everything. So down here, we were showing that our, well, both of these guys can close the file descriptor. I think that's kind of a stupid, yeah, this is, I don't know what they're trying to do here. It's like, they fork the child process, and then they both just close the pipe and do nothing with it. That's cool. But in any case, this would be, we could replace this word pipe here with a socket and pretend like these two processes are on different different computers on the internet. Okay, and we're getting effectively the same thing. All right, so let's keep trucking here. So we saw last time I/O on pipes. We have both our read and our writes, and we just use the normal thing. We do have a limited capacity on these guys, 4,096 bytes early on, and then we have 65,536 bytes after that. That's just the size of the buffer, because effectively what's a pipe? It's a buffer of memory. It may even be implemented as an abstraction of shared memory. Probably is implemented as an abstraction of shared memory. And we can pass a total of 65,500 that is likely, oh, no, that's right, 65,536 bytes, 0 to 65,535. So 65,536 divided by 8, that's bytes, divided by 1,024, that's kilobytes. Oh no, it's already bytes. It's already bytes. Sorry. So 65,536 bytes divided by 1,024 is kilobytes. Divided by 1,024 is megabytes. So let's leave it at kilobytes. So 64 kilobytes is the size of a pipe. So we're probably not, at least in a single. Well, let me ask it this way: could we transfer a 10 megabyte image from one process to another using pipes?
Could you?
Yeah. Limit is 64 kilobytes.
You'd have to break the file up and send parts of it.
Well, do you break the file up? How would you break the file up based on what we know so far?
Just a bunch of zeros and ones. Send some zeros and ones.
Byte 0 to 65 whatever, and then from byte 65.
Well, how do you do that though?
You've done it.
We have done it. You're right. We don't have to do anything special, do we? We just create a buffer that's not bigger than 64K, and we say we want to fill this buffer. How much do you want to read? I want to read up to 64K. So up to 65,536, and it will read as much of the file as it can, picking up for where it left off. And at the end you'll probably get a not quite 60, and then when you also read, you get how many bytes were read. We get that, don't we? So then when we write, can't we then write a certain number of bytes? So we have our buffer that might be half full when we get to the last big chunk, and we can go ahead and say, oh well, now I'm gonna write this thing. How much I'm going to write? Whatever's left, whatever I last read, and I'll write that over the network. The guy on the other side is going to be reading from that pipe, a certain amount of data. Make sense? So we don't have to do anything special. We don't have to break the file up. Our generic universal I/O already reads and writes stuff in whatever size we say. So now if we're on a local computer using pipes and we're reading and writing, would you want to use 64? Would there be anything wrong with using the maximum size of the pipe? You have 64K to work with. And if you have a 10 megabyte file, is there a major issue? Like, are we going to miss 64K of shared memory? It's getting reserved anyways, right? Like when we built the pipe, we didn't say, make sure it's this big. We just said, make me a pipe. So it's going to give us, in the newer versions of Linux, it's going to give us a 64K pipe. Memory's been used. We might as well take advantage of it, right? And if we're local on a machine, that's probably a decent idea. What about sockets? We have to assume sockets are probably going to follow some of the same rules as pipes, right? So would we want to, if we're sharing that file over the internet using a socket, we want to do 64K? Well, why not? So this kind of comes down to that decision making of, why we might use smaller buffers than we potentially could. What is the argument why we wouldn't want to send that file over the internet 64K at a time?
One 64K chunk is messed up or something wrong, then you're missing 64K instead of 10K.
Yeah, but that's not assuming we're using not the datagrams, but we're using the stream sockets that default over TCP/IP. 64K, it'll get there. Or if it doesn't, nothing got there. It's not like our file will be half there. But I mean, you make a good point. If something did go wrong, let's just make the assumption something could happen, right? If something did go wrong, even if it arrived on the other end and then got corrupted in some way, part of the deconstruction process. When your 64 bytes arrive at the destination and they start taking it out of the network module and start saying, okay, well, I'm going to write this now to a file, something could go bad. Maybe your file system hiccups or something like that. So even though the data all arrived, when it was being reconstructed, something went south. So his argument would be reasonable in that case, where he's saying, we'd rather not have 64K damaged. Maybe we want to have 8K damaged at a time as a max. Fair enough. What other reasons might we not want to do 64K at a time? Speed, tell me about that.
Wouldn't it take longer, depending on upload and download speed, the internet and everything?
between the two places.
Yeah.
Yeah, so, well, you say take longer. It should take, relatively speaking, the same total amount of time, right? So when you say take longer, where would I feel that? And I mean that in a creepy way. So if I'm the user on the receiving end and I am, we're reading at 64K at a time, how would, if that was too much, you know, you're concerned about performance, how would I notice that?
Not able to receive the next 64K before you finish doing what you need to do with the current 64K. So you could be getting it faster, but you're not because.
Okay. So this comes down to blocking versus non-blocking communication. Reading from a socket is blocking. Okay, so if I attempt to read 64K from a socket, and there isn't 64K there, okay, how do I say this without it being just completely horrible? I'm essentially going to be sucking on the socket, you know, until I finally get 64K of stuff. This subject should just be outlawed. There's all sorts of issues with this. Okay, so if I've asked for 64K, and that's what I'm going to try to read, I'm not going to move past that line of code until I have 64K. Depending on the internet speed, you know, 64K, now it probably, I mean, our modern internet connection speeds are pretty fast. I mean, 64K is not a real big file by today's standards. So how long does 64K take to download at Concordia? Anywhere between some fraction of a second and a week, right? Somewhere in that, you know, that range. But the fact is if I was only waiting for, let's say, a byte, I would, on average, have to wait less time, right? All right, so if the internet is somewhat slow and the data is kind of trickling in, and my application is trying to read something, and you know, especially with image files or video files, you can display part of it. You know, if you've ever listened, or audio, same thing. If you've ever started downloading, streaming audio, you know, as soon as you have enough of the stream, you can start listening. As long as the rest of it can keep up, you know, it comes in. It's a serial type processing. Cheerios, hashtag Tylenol, Christian worldview. So, brought to you by Nabisco. So the idea here is that 64K isn't all that much, but from a user's perspective, if we're sitting on the computer that's receiving that data, our application might feel paused because a socket read is a blocking type communication. We're not going to work past that line until we have our 64K. So does that mean we go on the other end? Do we read 1 byte at a time? It seems like Universal I/O seems to minimize us at a byte. So that seems to be the case, right? All the size of reads doesn't let us say I want to read a fraction of a byte. It's kind of a byte's our lowest common denominator. Seems to be our experience, right? So maybe we read that 10 megabyte file 1 byte at a time. Should we do that? What's the downside with that? Well, most images are going to be bigger than 64K as well, or at least there's a, you know, that's not that big. What would be the downside? Let's start with this. Could we read it in 1 byte at a time?
Yeah.
It would be accurate, correct? Okay, and we would get rid of that that feeling that our application is pausing, right? Because it's not. If we can't read in one byte is the smallest we can read in anyway, so that's going to be the minimal amount of time we could wait for that call to finish. Fair enough? All right, so now we're reading in 1 byte, doing whatever we're going to do with that byte, and then reading in another byte. Okay. What might we do with that byte? Let's say it's an image. Probably, are we going to be storing that? Are we going to be showing that byte on the screen? Are we going to be storing that byte into a file? Maybe writing it out to a file? Okay, so we're going to write to a file, let's say. So if we have a 10 megabyte file and we're reading it in 1 byte at a time, how many writes are we going to have to do to that file? Oh, 10 megabytes. That's that's that many kilobytes. That's that many bytes. So we're going to be doing 10,485,760 writes to that file. Okay? Is that a lot of writes? Well, from a human perspective, that seems like a lot. Is 10 million that big for a computer?
For one image file, maybe.
Okay. Is our file system one of the faster things on our computer? Probably one of the slowest things in our computer, right? So now, instead of your application being sluggish here, you're spending a majority of your time, what? Let's go back to the operating systems course, which this course most closely relates to. This is the programming side of the operating systems course, right? So if I'm writing to a file 10 million or 10.5 million times, what does that mean I'm doing 10.5 million times? Context switching. And is context switching bad? Slow. And how long, relatively speaking, how long do you think it takes to do the logic, the number crunching part of calling the read and the write universal I/O calls? Probably less time than that. Yes, I mean, not a whole lot. So we're probably not getting anywhere near our money's worth for the amount of time our process spends on the CPU before it's interrupted to go and write something again. So we're going to be context switching most of the time. So reading this file in 1 byte at a time is going to translate into a horribly inefficient version of getting that output written to the file. Because we're going to interrupt our CPU 10.5 million times in order to write 1 byte at a time. If we decide to write 2 bytes at a time, we only have to interrupt our CPU 5 million times. Okay? 2.5 million times, we do 4 bytes at a time, so on and so forth. Okay? So where's our sweet spot? How do we pick that number?
1,500.
Just arbitrarily?
Undecided.
Oh, okay. Okay, so 1,500 bytes. So you want to read in the maximum size of a single cell on the Ethernet. All right, that's fair enough. Since that's what if we have to unpack that anyways, if the TCP/IP stack has to unpack the single packet anyways, we might as well make sure it's it's full. Otherwise, it's like taking a semi-truck across the country to deliver 1 gallon of milk, right? You got to open the door anyways. You might as well have it full of stuff, right? All right. I think that's a reasonable enough answer. We still might have some performance issues that are all related to what we're saying, but hopefully what we're getting out of this is there isn't a clear answer in terms of the best. Where's that sweet spot in the middle? So his suggestion, which is pretty reasonable, is let's at least take full advantage of our TCP/IP packets. Reasonable enough. We're opening it anyways. Let's fill it. If we have sluggish internet, it's going to feel slow anyways. If we're still going to be context switching, but that's, as we talked about last semester, that's a necessary evil, so on and so forth. All right, so here's our named pipes. So anonymous pipes can only be used by related processes. So processes that one was a child compared to the parent. So that's what we dealt with last time. We had our file descriptors that were created. Bucket 0 was the parent, bucket 1 was the child, so these guys have, actually it's the other way around, 1 and 0. So unnamed pipes or anonymous pipes are only between relatives. But now if you want to share information between multiple processes, and now what you have to do is you have to name the pipe so that those processes can talk to the operating system specifically to become part of that communication sharing. Okay? So first in, first out pipes This is just a queue buffer. We don't have to think about any different, but these are a pipe with a name in the file system. So here's our creation, make FIFO, path name and permissions. So that's, you know, who's allowed to deal with it. Any process can open and use a named pipe. And the I/O works the same as it does for pipes because we're actually using universal I/O to work with these guys. So just like open, when we open something, open locks until other end is open. So we can't read from it until the other side of the pipe has also been opened and somebody might be writing to it. So we make sure both sides that a connection's been established. All right, we're going to skip message queues for right now. And we'll come back to that. Message queues is kind of like a post office. Already talked about shared memory. We're probably never going to talk about that. I might talk about that, but maybe not. Probably not. And we did confirm that sockets are in here, right? Or is that not a thing? Because I would have expected them to be up there with the other thing. Oh, there we go. Okay, so I guess it kind of makes sense to have synchronization talked about before sockets. We'll come back to synchronization. We've talked about it a little bit, but because when we're dealing with things that are happening across multiple machines, synchronization might be a bigger issue. So if we have 10 computers all writing to the same single database and that database is on one machine and those 10 other computers are all talking to it, synchronization might be a pretty important component of protecting the status of your data or something like that. That doesn't mean it's not important on a local situation. In fact, it's probably more likely to have missed data on a local machine because these things are happening so quickly together that something could kind of get in there and do a read or do a write, more importantly a write, before somebody else was done with the critical section. So sockets, as they're pointing out here, this is a big topic. Big topic. At least it's not as bad as the div problem from the other night. That's just the new thing, hashtag div, and that's an inside joke thing. There was an incident.
Okay.
Tried typing the HTML tag div, div, very late at night. And notice on your keyboard what the V is close to.
Spoiler alert. Big one.
All right, so
You just use text editor with autocomplete.
was I using one of those? I was using one of those. Those text editors can't keep up with me.
Plus it's a 3-letter.
What's this? All right, so we'll stop there. You will have a quiz on Monday.
Isn't Monday review for midterm?
Well, we'll review for the midterm after we talk about the quiz, after we have the quiz. The quiz will be on sockets. All 100...
On what we just talked about, or like?
The quiz will be on something we discussed today. All right? Midterm. We'll talk about the midterm on Monday, but the midterm will be in class on Wednesday next week.
We don't have class on Friday now?
Huh? We will not because I'll be traveling.